Cylinders and quadric surfaces. When graphing in 3 dimensions, a cylinder is a surface that consists of all lines, which we call rulings, that are parallel to a given line and pass through a given plane curve. So one thing that's important to realize is that a cylinder, when graphing, is not necessarily the same as the cylinder that you might be thinking of, which, of course, you know is a shape that looks something like this. So a cylinder is a more general classification of types of graphs. To illustrate this, let's consider the first example. Sketch the graph of z equals x squared. One of the defining features of a graph that's going to end up being a cylinder is that one of the 3 variables will be missing in this equation. So let's consider if we were just graphing in 2 dimensions, z equals x squared, where this is the x-axis and this is the z-axis. We know that this graph would essentially look like this. So we can transpose that graph onto the axis over here. Here is the x-axis, and here is the z-axis. And we can make some marks on here to make this a little bit more accurate. So here's x equals 1, x equals 2, x equals 3, negative 1, negative 2, negative 3, and then z equals 1, 2, 3, 4, 5, etc. So when x equals 0, z equals 0, that is this point right here. When x equals 1, z is equal to 1. So if I go to the x-axis at 1 and then up on the z-axis at 1, that's this point here. And what I'm doing right now is I'm basically just assuming that y is equal to 0. So I'm just taking this graph here and I'm going to transpose it over here onto the x and z axes. When x equals 2, z equals 4, that will be right about here. X equals negative 1, z equals 1, x equals negative 2, z equals 4, and that graph looks something like this. Now what we're going to do is we're going to pick other values of y, and then we're going to have the same plane curve for x and z. So for example, if I choose y equals 3, we will have this same graph, but moved over 3 units in this direction. So if I just slide all these points down 3 units, I get the following. And if I were to choose y equals a negative number, like say y equals negative 3, I would get this same graph, but just sliding down on the y-axis to negative 3. And now if we connect these sort of corresponding lines here, you see that you get this sort of surface. And it's kind of difficult to see in the graph that I've drawn here, so what I'll do is I'll bring in a nice picture of this graph. And so now you can see this graph a little bit more clearly. So here is that first parabola that we graphed, z equals x squared. Here is one where y is a positive value. Here is another one where y is a negative value. And what you see is that this surface is parallel to the y-axis, right? If you take any one of these lines here, it's all parallel to the y-axis. So this is what we call a cylinder in 3-dimensional space. And in this case, we can call it a parabolic cylinder because the cross sections are parabolas. Let's try another example. Part A here. Let's sketch the graph of x squared plus y squared is equal to 1. Now we can see that the variable z in this case is missing, which means that this graph is going to be parallel to that z-axis. So in 2 dimensions, we know that x squared plus y squared equals 1 is simply a circle of radius 1. So in the x-axis and y-axis over here, I will attempt to draw the same thing. So if we go 1 unit in all directions here, you can see that the circle in the xy plane looks something like this. Now that would be the circle where z is equal to 0. But if I choose a higher value of z, I would get that same circle just graphed at a higher level. And if I choose z equals a negative number, I would also get that same circle, but then just graphed at a lower level. And so if you take a look at what we have here, and maybe if I dot the line behind here, it might be a little bit easier to see. But we essentially get something like this. And of course, this goes up forever and down forever. Now this one is actually a cylinder, right? This is the kind of cylinder that you think of when you hear the word cylinder. And it is an infinitely tall cylinder, right? Parallel to the z-axis. And I'll bring in a nice picture of this one as well. And one thing that is important to emphasize is that when sketching three-dimensional graphs, this is often very challenging for students to do. It's even challenging for myself to do. So we don't need our graphs to be perfect. And also, this is where technology can really lend a helping hand. There are some 3D graphing calculators available that makes these pictures really nice compared to what we can draw by hand. And that being said, some people are actually really good at making these graphs by hand, but most people aren't. Let's try the second example here. So in part B, we have y squared plus z squared is equal to 1. And this is going to be a graph parallel to the x-axis. Notice that it's going to be pretty much the exact same type of graph as what you have here because the equations are pretty much identical. It's just that we have the variables y and z instead of the variables x and y. So we know that when you have an equation like this with two variables, the relationship here is describing a circle. So what I'm going to do here is graph a circle. This will be in the YZ plane, and it's just going to be a circle of radius 1. So if I go 1 unit on the y-axis in both directions, 1 unit on the z-axis in both directions, that circle is going to intersect the y-axis and the z-axis as such. And then if we choose x equals a positive number or a negative number, because this one here corresponds to x equals 0, we're just going to get additional circles, right? So it's just going to look something like this. And over here, it's just going to look something like this. And then we're going to have a cylinder laid on its side going forever in both of these directions. And let's go ahead and bring in a nice picture. And there you go. So it's pretty much exactly the same as this other surface, but just sideways. Next, we're going to talk about quadric surface. So a quadric surface is the graph of a second-degree equation in x, y, and z. So the most general form of this equation would look something like this. So notice that we have second powers of x, y, and z. We also have the variable x times y times z, x times z, and then x, y, and z by themselves to the first power, and then also a constant here. Now, most of the time we will not be graphing things that are this complicated. In fact, most of the time we're going to be looking at things where we eliminate these other terms, and we're just going to be looking at something a little bit more simple, such as ax squared plus by squared plus cz squared plus j is equal to 0. Or sometimes instead of the variable z squared, we'll just have the variable z. These are the two standard forms that we're going to be considering in this class. Quadric surfaces are basically the counterparts in 3 dimensions of the conic sections that you learn in 2 dimensions. So things like parabolas, ellipses, and hyperbolas. Let's go ahead and take a look at an example. So here we want to graph the quadric surface that has the equation x squared plus y squared over 9 plus z squared over 4 is equal to 1. And the way we're going to do this is we're going to consider traces. So to do this, what I'm going to do is let one of my variables be equal to a constant k. So let's assume that the variable z is equal to some constant k. If I do that, the equation can be reduced to x squared plus y squared over 9 is equal to 1 minus k squared over 4, where k is a number. Now let's keep in mind that on the left-hand side, this is always going to be a positive quantity, which means that k squared over 4 cannot be bigger than 1, because if it is, then you will be subtracting something that's bigger than 1, and this will be a negative number, which would give you no solution. So because of that, k must be a number in between -2 and +2. And that actually means that on your graph, since z is equal to k, z has to be a number in between +2 and -2. So let me go ahead and put that on my graph. So there's z equals 2, and there is z equals -2. Now think about what this graph looks like. Okay, so for example, if k is equal to 0, we're going to have x squared plus y squared over 9 is equal to 1. Now k equals 0 is the same as z equals 0, which means this would be happening in the xy plane. Let's remember that this in 2 dimensions is an ellipse. And what this would look like is an ellipse that goes out 3 units on the y-axis and 1 unit on the x-axis. And that particular ellipse would look like this. Now, if I choose other values for k, we're going to get other ellipses. So for example, if k is equal to 1, we'll have x squared plus y squared over 9 is equal to 3/4. And then what you would have to do is multiply both sides by 4/3 to kind of put it in standard form. And I don't want to go through too many of the details here, but basically it would look like this. And what this would give you is just another ellipse, but it would be a little bit smaller. So on the x-axis, it would not go out as far as 1, and on the y-axis, it would not go out as far as 3. And the z-axis, of course, it would be at 1 now, because if I choose k equals 1, that means z is also equal to 1. And it is going to be a smaller ellipse that kind of looks like this. Now, if you were to graph more of these things, what you would find out is that these ellipses stack up from z equals 0 up to z equals 2, and all the way down to -2. And this is the graph of something that is called an ellipsoid. And what I'll do now is I'll bring in a little better picture of this. And there it is. Now, when you're doing other equations, it might be necessary to let other variables be equal to k, because a lot of times your cross sections are not always going to be similar. So in this case, we can get away with it because we had an ellipse here, an ellipse stacked up here. So you can see that all of the cross sections, if you cut this thing this way, are just going to be these ellipses. And so this is what we call an ellipsoid. And I guess what you can think of this as is it's kind of like an egg. All right, let's take a look at another example. In this next example, we want to use traces to sketch the surface z equals 4x squared plus y squared. And this surface will be a little bit simpler than the last problem. So let's go ahead and use traces by letting y equal k. And then z will equal 4x squared plus k squared. Now we know what the graph of z equals 4x squared looks like. That's just going to be a parabola. And so this would be what it looks like when k equals 0. If k is any other number, positive or negative, when you square it, it becomes positive, which means the graph is just going to be the same parabola but moved up a particular quantity. So k, if k is not 0, it's going to look something like this. So what that means over here on the graph, remember y is k, so if y is 0, you're going to get z equals 4x squared. If y is equal to some value over here, it's going to be a parabola again, but it's going to be moved up a little bit, so it looks like this. If y equals a value over here, it's going to be moved up as well. And if you start to connect these things, you start to see a three-dimensional surface. But again, this is very difficult to draw. Now, what I can do also here is I can let x equal k. And in that case, z would simply be y squared plus 4k squared. And this is also a parabola in the z and the y-axis. And so that would be parabolas that you would be graphing in this plane. And those parabolas would look very similar to the ones that we have here. So no matter if you're taking cross-sections parallel to the xz axis or cross-sections parallel to the yz axis, you're getting parabolas all the time. And this is what we call a paraboloid. And let's go ahead and bring in the picture. So this is actually what we call an elliptical paraboloid because we have parabolas this way. So cross-sections taken that way are parabolas. But if you take cross-sections this other way, you are getting an ellipse. And to see that, what you could do is you could just let z equal k, and then 4x squared plus y squared equals k would be an ellipse. For the next example, we could do the same thing. What I want you to notice is that if we were to let x equal k, we would have z equals y squared, which is parabolas. If we let y equal k, we would have z equals negative x squared, or negative x squared plus k squared, which is also parabolas, but they open downward. And then if I let z equal k, we get hyperbolas. So when you have something like this, it is very difficult to try to graph this by hand. And I'm going to go ahead and bring in the graph and try to point out some of the features. So as I mentioned, if we let x equal k, and you start looking at z as a function of y, you would get z equals y squared minus k. So what you can see there is you basically just have parabolas. And so if I look in the yz plane, you can kind of see one of those parabolas right there. In fact, that's the one that would correspond to k equals 0. If I let this should be k squared. If I let y equal k, I get z equals k squared minus x squared. These are going to be parabolas as well in the xz plane, but they are going to open down because you have a negative x squared. And that's this one right here. And then if you let z equal k, you end up getting y squared minus x squared is equal to k, and this is a hyperbola. And so if I let z equal a number like, say, 1, you can see that in the xy plane, you are getting hyperbolas. And so these are the ones that are kind of opening sideways like this, and then you have a mirror image over here. So again, these graphs are really tough to draw, and usually we don't require our students to draw graphs like this because they take a ton of practice, and I also think you have to have some artistic ability to be able to sketch these things accurately. So now, as a summary of types of quadric surfaces, you could pause the video here and read this yourself, but we have ellipsoids, we have paraboloids, we have cones, hyperboloids with 1 sheet, hyperboloids with 2 sheets, and those have to do with how many negatives you have in the equation. And then we have what's called a hyperbolic paraboloid, which is the graph that we just did. And these are all the different types of equations that lead to these types of graphs. So in this next example, sketch the surface that you see here. Think about which category this falls into. So according to our list on the previous page, you can see that this equation exactly fits this model. And so we have a hyperboloid of one sheet. The one sheet, you can think of that as this is all one continuous graph. So this surface is all completely connected, as opposed to the one with two sheets, you have two distinct disconnected graphs. But we know that this is going to look something like what you see here. And then the numbers that you see down here are just going to determine the shape of this graph. So let's go ahead and bring in a picture. So here it is. Notice that you can find out some of these trace curves. Like if you let z equal 0, you get x squared over 4 plus y squared equals 1. That's an ellipse. So that's the ellipse that you would see right here. And then if you were to let y equal 0, in the xz plane, you have these hyperbolas that are opening like this. And if you were to let x equal 0, you would have a hyperbola in the yz plane. And those are the ones that you see opening over here. Okay? So you have hyperbolas opening this way, but if you take cross sections the other way, you get an ellipse. Now in this next example, identify and sketch the surface. Again, we're not going to focus too much on sketching the surface, but we would like to identify what we have. So for this, I'm going to rewrite the equation here, 4x squared minus y squared plus 2z squared equals -4. And the way to identify these is you want to have a positive 1 over on the right-hand side. So I'm going to divide everything by -4. On the left-hand side, that gives us -x squared plus y squared over 4 minus z squared over 2 is equal to 1. And so now this is an equation that has two negatives. And so this will be a hyperboloid with two sheets. Let's go ahead and bring in the graph. And so there it is, and you can see that you have some points here where these hyperboloids begin and end, but most importantly, you should see that you have two disconnected graphs, and that is because we have the two negatives in the equation, and thus we have the two sheets. Now you can see that the cross sections that run this way are ellipses, and the cross sections that run the other way are hyperboloids, and the cross sections that run this way are hyperboloids. So that is to say the cross sections parallel to the xz axis are ellipses. The cross sections parallel to the xy axis are hyperboloids, and the cross sections parallel to the yz axis are hyperboloids. I think I might have said paraboloids. I meant hyperboloids. Again, don't worry too much about graphing these. In fact, I would highly recommend that you find a 3D graphing calculator and try to sketch some of these things just for fun. In our final example, we want to classify the quadric surface that we have here. Notice the equation is a little bit more complicated. So I will focus on rewriting this by grouping my x variables together. And then I have plus 2z squared plus 10 is equal to y. If I complete the square here, I get the following. This, of course, turns into x minus 3 quantity squared plus 2z squared plus 1 is equal to y. And what you can also do with that plus 1 is you can move it over to the other side with the y. And this is going to be a paraboloid. In other words, it's going to be a three-dimensional looking parabola, something like this. But in which direction does it go? And where is it located? So let's attempt to sketch this one. So first of all, notice that y is a function of an x squared and a z squared. So the paraboloid is going to run parallel to this y-axis. In fact, if we did not have the -3 and the -1, this paraboloid would essentially start here, and it would open up in this direction. It would look something like this. The -3 is going to translate the graph 3 units on the x-axis in the positive direction, and the -1 with the y is going to translate it 1 unit this way on the y-axis. So if I translate that graph, the vertex of this paraboloid is going to be out here, and it's going to open as such. And now we'll go ahead and bring in a nice picture. All right, so you can kind of see what we're talking about there. This point is this point here, and it opens kind of parallel with the y-axis. To conclude here, we want to be able to sketch some of the more basic curves in 3 dimensions, but some of the more challenging ones are very challenging. And don't worry too much if you're not really great at sketching these more challenging curves. We're going to be using 3D graphing software most of the time to help us anyway. And that concludes this video lesson.